Okay, so our second talk, in a similar vein, will be given by Benjamin. First principles models to predict the evaporation and crystallization of a saline droplet.
Thank you very much. So I'll be presenting to you the work I've been doing on the evaporation and crystallization model for a saline droplet. Right, so I've been working on developing a mathematical model for the evaporation of a saline droplet, and the goal is to compare this model with experimental data. But at the same time, I've been working also on a crystallization model, and my goal there was to try to be able to predict the number and size of the crystals from the dry residue of the saline droplet at the end of evaporation, and see if we could compare this with SEM images. Now, for that, I've used parameter estimation matching on the crystal birth and growth rates from the crystallization model. So I'll be considering a single droplet containing water and sodium chloride, which is just evaporating in ambient air. And so I have quite a few equations in this presentation. So I'll try to explain each term in these equations and what these equations do without getting too much into the details. Right, so the first equation is about the change in droplet mass as a function of time. And so this is given by the product of the droplet surface area with mass transfer coefficients and a concentration gradient of water vapor between the surface of the droplet and far from the droplet. Now we can re-express some of these coefficients, the mass transfer coefficient and the concentration of water vapor, using some known parameters, and this gives us actually our first differential equation for the change in droplet size as a function of time. Now, very similarly, we can do an energy balance on the droplet, and this energy balance gives us three terms. The first term is the convection term, which is very similar to in the previous equation, is the product of the droplet surface area with a heat transfer coefficient and a gradient of temperature between the droplet and the air from the droplet. Now, there's two additional terms to this energy balance, which are due to the change of phases occurring inside the droplet. So the first is the heat loss due to evaporation. This is for the water inside the droplet going from the liquid phase to the gas phase as the droplet evaporates. And the second term is the solute, in our case, the sodium chloride, going from the aqueous phase to a solid phase as the droplet crystallizes. Very similar to previously, we can re-express some of these terms, not going into too much details, but then we can get each of these into known parameters. Right, so as was mentioned by Barney just before, so as the droplet evaporates, it therefore shrinks, and then the solute sodium chloride doesn't evaporate, so it starts to get an enrichment of the solute at the surface of the droplet, which then diffuses toward the center. So in order to solve this numerically, I've been dividing the internal domain of the droplet into a few different control volumes that we can call cells. And by using the spherical coordinates, I can get fixed lower diffusion to get the information on the change in concentration that occurs inside the droplet. So there's two terms in this equation, a diffusion term, but also there's a sink term, which is due to the solute going from the aqueous phase to the solid phase. So this reduces the concentration of sodium chloride. This is given by a certain term called the solid volume fraction epsilon, which I will detail a bit more later on. This is a partial differential equation in time and space, so we need boundary conditions. There's first boundary condition at the droplet center given by the symmetry, and at the droplet surface, which is given, which I get by performing a mass balance on the droplet. Right, so this is one of our first partial differential equation, and then moving on to the crystallization modeling. This was solved using this was done by solving the population balance equation, which, as the name implies, gives information of a population of particles And in the case I'm showing here, there's only two terms for the change in crystal number density. So there's first a diffusion term and a second a growth term, so the crystal growth in size. You may have noticed here, this is a partial differential equation in time, in space, the position of the control volume, and also in crystal size. So that means that in addition to the boundary condition I've shown earlier for the solid concentration, we also need a boundary condition for on a crystal size, and this is given by what's called a Dirichlet boundary condition, where we get the information on the crystal number density for the smallest crystal size that we take into account. And this is related to the birth and growth term. So these birth and growth terms are expressed as a function of the difference in the solute concentration and a certain critical concentration that I've called here, the crystallization concentration. I've left in, so I've used like power law models for these birth and growth terms, and I've left the constants and exponents as unknown, and this is what I'll be using some simulation and parameter estimation machine on to try to estimate these constants and these exponents to try to see if I can match certain properties that are visible on the SEM images. Now, because this is a partial differential equation in space, but also on crystal size, that means that on top of, in addition to the discretize the internal domain of the droplet in multiple control volumes, we also need to discretize all the crystal sizes in a certain amount of bits. So that would give us some information like this number density and function of crystal size. But that means that we need to solve for each of the crystal sizes. We need to solve these equations in each of the each of the control volumes of the droplet. So that really increases the amount of equations, and so this would take a really long time. So another way to solve the population variance equation I've just shown in the previous slide is to use the method of moment. So first I'm describing here the relation for the diffusivity of these solid particles, which are a function of the crystal size. And then I will define 4 moments, so M0 to M3, which are given by the integral of all crystal size that are shown here for a specific moment of all the A, just shown on the left-hand side. And on the right-hand side, I'm showing all the 4 different moments which are useful for my equations, which give information on the total number of particles per unit volume, total length, total surface of particle, and the last one, the epsilon, which I've shown earlier, which is the volume fraction of the particles. So this is how much space these particles take inside each of the control volumes of the internal discretizations of the droplet I've shown earlier. Now, by taking the integral on crystal size of the previous equation, the population variance equation, we can get a differential equation for each of these 4 moments. And so this allows to reduce the number of equations of how to discretize for a certain amount of crystal bins to only 4 equations for to get each of these moments. And this greatly reduces the amount of equations needed to solve. Now, as you remember, there was the crystal birth and growth terms were a function of the difference between a solid concentration and a certain critical concentration. Now, to get the information on this critical concentration, I've been using X-ray diffraction on the acoustically levitating droplets. So you can see on the top right that there's the equipment where an X-ray beam would be coming from the left-hand side, going through a droplet that would be levitating through acoustic levitation and going on to the sensor, and this X-ray beam would be detected on the sensor, which is on the right-hand side. So we can do this as the droplets evaporate, and then we can get, as I'm showing here on the bottom right, a 2D diffraction pattern of the droplets. And we can, if we know the initial concentration of the droplet and also the change in the size of the droplet as a function of time, we can estimate what was the concentration when the first crystals start appearing. So this is what I've been using in my crystal birth and growth terms. Now, by performing quite a lot of simulations, I've been I've come up to now to these birth and growth parameters, which are a function of the solute concentration with the critical concentration. And so the goal here was to first of all match the evaporation predicted by the model, which is shown in the blue line on the bottom left here, and to see if that will match the measurements from the acoustic levitator. So in this case, we had quite a good match of the final size of the solid particle and the time that it takes to reach this final size. Well, the second thing I was trying to do at the same time was to be able to see if I could match the number and the size of this crystal with SEM images. So this is still work in progress. There's still more to do, taking more SEM images to see what are the differences, if we will get the same crystal size and the same number of crystals if I were to do many evaporation of droplets. This is still some work in progress. But I will finish with the last slide comparing the method of moments that I've explained in this presentation with a fully discrete moment, fully discrete equation for solving the population balance equation. And so on the left and right hand side, I'm showing the volume fraction and function of the radial position. And in terms of, there's quite a good match between the time to reach the size, the final size, and the final size of the droplet. And as well, like the capital M0 and average size. Capital M0 is the total predicted amount of crystals, and the average size is shown as well. And so there's quite a good match, and we can see that this really greatly reduces the method of moment, greatly reduces the amount of equations and also the computational time, which allowed me to perform a lot of simulations in much less time. So that was my presentation. So thank you very much for your attention.
Thank you very much, Benjamin. 2 talks on droplet drying, and obviously in terms of the pandemic, were absolutely crucial in terms of understanding physical distancing and the drying of respiratory aerosols. So great to see this field pushing forward. Any questions?
Very interesting talk. I really like the tiny left X-ray combination. I was wondering, is the assumption that crystallization starts homogeneously sort of inside the middle of the droplet? Are there any systems where it would preferentially crystallize at the edge?
Yeah, and actually that's very likely to happen. It's very possible that indeed the crystallization would start on the surface of the droplet, because this is where we have the high supersaturation of the solute. Now, so the X-ray beam has a certain thickness, and it would go through the front and back of the droplet. The only thing is that what we will also notice is that due to gravity, some of these crystals would fall to the bottom. Yeah, this is what we've come up with to solve this equation. But indeed, yeah, there's a few assumptions taken here.
So I have a question just so you I guess you have quite a nice model for looking at diffusion and limited kinetics in the bulk of the droplet as well. So actually a droplet as it dries changing in viscosity, changing in heterogeneity as a result of that. Am I right? Is that direction you can go with this model?
I've not really looked at change in viscosity, but indeed, yeah, the whole goal of this model was to see like how the solute diffuses, and indeed, depending on the evaporation rate, we would see diffusion of the solutes towards the center, or actually quite a large enrichment of the solutes towards the surface. But yeah, I've not really looked at other properties such as viscosity, surface tension.
In principle, you could That's a step.
I wonder, yeah, if there would be a way to get surface tension as a function of solute concentration. That could be done, yeah. Maybe if we were to measure, yeah, indeed the viscosity, surface tension, and other properties with different concentration of salt, that could possibly be done.
More questions? Someone-
Just very quickly, how do you interpret the data? I see a pattern, a diffraction pattern. Are you able to resolve inside the droplet? Are you getting an average concentration? Can you just explain how the technique works? What's the resolution?
But
You have concentration there. Is that
yeah.
average concentration?
Right, yes, so that's a good point indeed. So this is something that I've sort of back calculated. So knowing I know the change in size of the droplet as it evaporates, and also know the initial concentration, as this is something I've measured. So I've kind of back calculated the concentration inside droplet, but indeed this is the average concentration. And it's very possible that, well, it is actually the case that the surface the concentration of solute at the surface would be higher than at the center. So I could also try to feed in this data directly into my model, which looks at diffusion of the salt, and try to see what was the concentration at the surface of the droplet. That's something I could do. Maybe get a better estimate of this critical concentration when crystallization starts happening.
Great. Thanks very much, Benjamin.